me consider let me continue the proof for k equal to 1. You can also extend it for k equal to 2 for any fixed k. When we fix the k, here we can observe that all terms belong to the corresponding place pk, because if we look at the valuation of each term, for instance, in this summand, that means v1 of phi of 2j ax 2 to the a. And here also I forgot to mention that depending on these indexes, we will multiply this equation by tk to the minus c. So in this case, we will multiply t1 to the minus c, t1 to the minus c times z1j. So after this multiplication, each sums belong to the place pk. And by applying the properties of the discrete valuation map, and regarding the fact that T1 is the prime element for V1 and we choose the prime element for P2, whose valuation at P1 is 0. And here note that these are the polynomials and the polynomial ring contained in OP. This has valuation bigger than or equal to 0. And finally, since we have chosen Zij with respect to weak approximation theorem, we consider here note that this Z2ij is bigger than or equal to E1. Then we can see that since we have fixed this C between 1 and E1 and minus 1, we can see that it is positive. So this shows that after multiplication T1 minus T1 to the minus C, this term belongs to the places P1. And similarly, we can also analyze if these terms, if this summand or each term belongs to P1 by checking the terms for the fixed j between 1 and E1. By the way, I made a mistake here in the notation. This is dk minus 1. So here we are in the case E1 minus 1. And when A is less than C1, like in the previous case regarding our assumptions, and for when A is less than C, we know that this is divisible by X. So that means it has 0, at least of order EK. And this is the prime element, so this is 1. We have A minus C. And by the assumption from, since we have chosen this Z1j from OP1, this valuation is also bigger than 0. And Since a is a positive integer, we can see that this is bigger than or equal to ek minus c, and this is also positive. When a is bigger than c, similarly, we can see that this is going to have positive valuation. From the prime element, we will get the factor a minus c, and similarly, these are the valuation rings OP1, they have positive valuations. So the valuation of this term is also positive. So after multiplication t1 minus t1 to the minus c, we can see that this term belongs to place p1. So now if we apply the residue class map, but before that, for the case a equals c, if we consider the term phi1 jcx, the polynomial, this polynomial from k of x times z1j. So since all these terms in the summit belong to pk, this when a is equal to c, this term should be also lies in p1. And here also, let me note that the evaluation of this polynomial at p1 belongs to k, and not all divisible by x. So that means not all has zeros at p. And here, if we apply the residue class map, to this function, we will obtain the non-trivial combination of the elements in the residue class field fp1. We will get the contradiction with the linearly independence of these elements. But here it's not so that trivial, because in the beginning we suppose that these corresponding Sij's are linearly independent in the residue class field. And then by weak approximation theorem, we choose the functions Zij's such that V1 S1j minus V1 of S1j minus Z1j is positive, and they have both at P2 of order at this E1. But only with this definition, we can see that if we are given F1 linearly independent elements, which are denoted by Sij of P1, and by this condition, we know that since the valuation is positive, that means this difference lies in P. So S1j, evaluation of S1j at P1 is equal to the evaluation of Z1j at P1. So if these Sij's are linearly independent, this chosen Zij's, I mean this chosen with respect to the approximation theorem, these Zij's are also linearly independent. So this is why we get contradiction. And as an important result, and as I mentioned in the beginning of this lecture, Actually, I stated that every transcendental is finite many zero and false, but here we can say that any element in an algebraic non-zero element in an algebraic function field has only finitely many zeros and false. Because if x is constant, it has neither zeros and false, because for all valuation v of x will be 0. And if x is transcendental, by proposition 113, we have seen that number of zeros bounded above the extension degree of the function field which is finite. And to see that a transcendental has finite many false, let me first observe that to have a pole at a place P mean that for a function x, its inverse has a 0 at the same place. So in this case, like similarly, we did for x, number of zeros of x inverse is bounded above this extension degree, and the number of the zeros x inverse and the poles of x are in one-to-one correspondence. We can conclude that also a function x has finitely many poles. So in the last video, I tried to motivate some new notions regarding the previous observations we had so far, and try to introduce what we call divisors. So see you in the next video. Bye-bye.